Alright, so we're back. This is episode 3 in the series. Um, so last episode, I finished up the sliding windows section. I did this minimum size subarray sum, and it took me a while because I just read the problem wrong. But I think I have a good understanding of sliding window. Um, So now I'm going to move on to the next topic, which is two pointers. So in sliding window, the two pointers, you got a left and a right, and left could never overtake the right. They could be on the same index, but they could never like overlap. And two pointers, I guess this is different. So the pointers can cross each other. Um, so I'll show you guys this spreadsheet so far. So this is what we've done. So this was last episode. I'm still counting it as May 7th, even though it's May 8th. I want to do one more problem today, before I call it a night. So we're just gonna go ahead and start on this sorting colors problem, which I have open here. I haven't really looked at it. I kind of just opened up the problem. I don't really know what it entails, but we will find out. So this time, I'm going to be sure to read the problem extremely carefully so I don't do the wrong thing. So yeah, let's go ahead and start. Alright, so given an array nums with n objects colored red, white, or blue, sort them in place. So this means that we can't create another array, I believe. We just have to modify the given array. So that the objects of the same color are adjacent with the colors in the order red, white, and blue. Okay, so it has to be in this order, red, white, and blue. And objects of the same color are adjacent. Okay, we will use the integers 0, 1, and 2 to represent the colors red, white, and blue, respectively. You must solve this problem without using the library's sort function. And that makes sense. I guess that would, using this would sort of trivialize the problem, right? So okay, let's look at some test cases here. So we have this array, and we end up with 0, 0, 1, 1, 2, 2. In this array, you get 0, 1, 2. So I guess, okay, yeah, so sorting would take n log n as a time complexity of n log n. I don't know what the time complexity of a two-pointer approach would be. But I imagine we have two pointers, right? I got this paint thing, so I want to try drawing on here, right? So what were our numbers? 2, 0, 2, 1, 1, 0. Can I just do this? 2, 0, 2, 1, 1, 0. And let me make this a little bigger. Right. Okay, so I'm imagining we have well, okay, so we know all the zeros need to go to the front, right? So maybe we start a left pointer here and a right pointer here. And what do we want to do here? My first thought was something similar to bubble sort, right? So putting L and R next to each other and kind of swapping them in bubbling. But that's just sorting, so I don't think that works. I don't think that's the optimal solution, right? What we want is we need to make sure that all of the zeros end up towards the start of the array here, right? So I think, hmm, this is interesting. Okay, what if we did start them next to each other? Just want to try this out, right? So you have a 2 and a 0, and I'm imagining we have some function that we make called like swap, um, which will take two like indices and then swap their positions in the array. So maybe like A and B. I'm imagining we have some function. We can create that, right? Um, so we have a 2 here and a 0 here. So those need to swap, right? But why do they need to swap? Um, I need to swap because, I mean, this 0 is less than 2, right? And red needs to go before blue. So we could swap these, yeah, and then we know that 0 is in place. And then, that doesn't make sense though, right? I'm going to try just writing this in my notebook. And I'll try to get good intuition just handwriting it. It's kind of slow to write it in Paint, so I'll try to explain the intuition on there. But for now, I'll just try doing it in my notebook. So I'm curious to see what this page says about two pointers. This is a more general version of sliding window, where the pointers can cross each other and can be on different arrays. Okay, yeah, so I think the easiest thing to do would actually just be to iterate through the input and then create a hash table of how many times each element occurs. So in the first one, 0 occurs twice, 1 occurs twice, and 2 occurs twice. And then just reconstruct a list from that. But the thing is, we have to sort them in place. We're not actually returning any value here. We're just modifying the original list. So let's see. Because also it says, because you come up with a one pass algorithm. So I'm assuming using two pointers, you only need to iterate through the list once, right? If you have to iterate through it multiple times, I don't think that's the most like optimal solution. Um, hmm. Let's see. So in our sliding window, we always initialized L and R to be on the same index. So they were both just at the start. And we iterated till R reached the end. But I don't know if that's necessarily true anymore because with two pointers they can overlap, right? Um, so my question is like, where do we start these pointers? Like, where should they begin in the array? Okay, so 0, 0, 1, 1, 2, 2. That's our end goal. How do you do that in one pass? Let's see. See, for the other problems, I at least kind of knew the intuition. For this problem, I just don't even know where to start. I just don't even know how this logic would work out. Hmm. Like, when do you increment or decrement the pointers? Because here's the problem. All the solutions that I'm thinking of are just sorting algorithms, which I don't think are correct in this case. Like, I just thought of like selection sort right now, just swapping them one at a time until they're in the right order. But that shouldn't be I don't think that's the optimal way to do this. I think the key here might be something to do with how we only have two elements. Or three different kinds of elements, right? We only have 0, 1, or 2. Oh, okay. I think I might have an idea. Okay, so we have L here and the R here. Oh, okay. I think I know how this works. Okay, wait. So we have L starts on the very left, R starts on the very right. And so we think, okay, if L is less than R, um, then maybe we don't do anything. But if R is less than L, then maybe we swap them. So we end up with 0, 0, 2, 1, 1, 2. Now L and R are in the same spot, but we know the 0 and the 2 are now in the correct spots. So we can check if L is equal to 0 or if R is equal to 2. Then we know that those are in the correct spot. And at that point, maybe we can increment L and decrement R. And then, okay, so the same thing happens here. So we know that L is less than R, but L is also a 0. So in that case, we should just increment it, right? So if L is on a 0, okay, so yeah, while L is a 0 or R is a 2, increment or decrement them, right? So now L is greater than R, so then we swap them. R is 2, so we decrement it. Okay, I mean, so that works for the first case. Here's the problem though. What if we only have like ones? Maybe we just have a list that's like 1, 1, 1, 1. L starts, R starts. So if they're both equal to 1, then what do we do, right? They're both not correct. And what we need to do is swap r with the value 2. Because if our array is 1, 1, 2, 1, we need to swap 2 to the end of the array. So how do we do that? Do we just keep moving L? Or what? Let's think. It's an interesting problem here. Okay, and again, like look at this test case where they have 2, 0, 1. If you start L at 2 and R at 1, well L is greater than R, so we swap it. And 1, 0, 2. Well, now we know R is on a 2, so we can decrement R to 0, and then that 0 and the 1 should swap. And then we increment L. And I guess the algorithm ends when L and R meet in the middle. The problem is, if that's our case of 1, 1, 2, 1, like, what do we do if both L and R are equal? Because they're both, like, who do you decide to change? If L and R are both equal, and neither of them are 1 or 2, right? So what do you do in this case? Because you don't know which one to increment or decrement, right? So that's why I feel like my logic right now is kind of wrong. Just how do you handle this case? You're not always going to have a 2 or a 0 that you can increment or decrement from. Like you might just have 1s and 2s, and you don't have any zeros. And what about the case, what if you have 1, 0, 2, 1? And what if you have that? Then what do you do? Because L and R are equal, how do you know who to increment? Now here's one solution I think of, right? You start L and R next to each other, right? And when R is greater, or R is less than L, so you would swap, and you get 0, 1. I mean, that's the thing, you just don't know where the zeros will be. You can't just tell like where they'll be. So that's why I'm getting confused here. Like, how is this supposed to work? Like, where do you set the pointers in the start, right? I think we should look at a hint. They have like hints on here, so I think I should look at them. A two-pass solution using counting sort. I don't really know what that is. What is this? Just not. So you are supposed to just use a hash table, no? I'm so confused. Why is this supposed to be 2 pointers? I mentioned my hash table approach here, right? I'm so confused. What? Okay, wait. Let me just code up this hash table approach first. I don't remember any of this. Okay, dictionary. idict. The keys are numbers though. Can you actually just change that? Oh wait, there's something called a default dict in Python, which I think would be useful for this, but I won't use it now. If num in table no. But basically what the default dict allows you to do is kind of avoid doing this if else, and it'll just initialize the value of the key to 1 even if it isn't in the dict. But I kind of forgot how to do that, so I won't. Let me think here. Okay, wait, what am I doing? Let me just make sure this works. Just run this real quick. Okay, yeah, that works. Then I'm pretty sure like this syntax works. Right? What did I do? How do you do access? Oh. .get. Okay, yeah, I should actually figure this syntax out eventually. Well, that's what practice is for, right? And I think they let you Google syntax in interviews. I'll slow you down. Okay, what am I doing wrong here? let me just create a test list. So I'm pretty sure this syntax works. Okay, wait. This is Python. Okay, yeah, you can't use a plus sign. Okay. Change this to 1. This to 2. See this, U list, J list. I know this is very messy, but I'm just very confused. So we can't just like overwrite nums. Okay. And nums I is equal to ki. Okay. So okay, I see how that works. Oh. Yeah, well, sometimes there isn't anything. Should I just do this? How is our runtime 0 milliseconds? Okay, this is a constant time solution. I'm confused though. No, I thought of this solution. I was just like, I think the reason I didn't do this is because I thought the memory footprint would be too big, right? No, I'm so confused though. What? Okay, now obviously you don't need to create K. Like, I think there's a more efficient way than just doing it, but I'm just so confused. What is the 2-pointer solution? 3 pointers. Dutch national flag algorithm. We need 3 pointers. Hold on a second. Can I pause this? Okay, so I found the relevant Leetcode video. So I'm gonna go through this, try to understand. He says in the title that is a quicksort partition. I vaguely remember how quicksort works, like from our DSA class. I guess I can understand how it would be used here, but I'm just confused because in the question it says don't use the inbuilt sorting method is doing quicksort not the same thing, right? It's just you're just writing your own sorting method instead of just using the built-in one. But I
nums as a
guess I'll just
color, but
watch
let's
it.
just skip that because I think it just kind of makes things a little bit overcomplicated. So let's think of it simply. We are given an array of nums and values in this array. Any of the values could be of 3 different integers. Each value could be a 0, 1, or a 2. We want to take this array and then sort it in ascending order, right? So let's say this is the input array. We want it to be in ascending order, zeros first, ones next, and then twos, right? Pretty straightforward, but there's many different ways you can solve this problem with varying efficiencies and varying memory complexities. So now they tell us right off the bat we can't use like a library sorting function because of course library sorting functions run in n log n time, and it would just be a single function call, just call sort on this array. But I guess we could implement our own sorting function, which would also end up being n log n, whether you do merge sort, or I think quicksort also has the same average time complexity, right? So we could implement our own sorting and then do it in n log n time, but we can see that this problem is a little bit more simple than just a regular sorting problem because we are given only 3 values in the array, only 3 potential values. So
Yeah, I
if
think
we
I
have
said
heard
this
of
while I was doing it initially. Like, there's only 3 colors, and that was kind of like the key to this being different than just normal sorting problem.
the algorithm bucket sort, then right off the bat, you're going to think,
Bucket
yeah,
sort.
this problem can be solved with bucket sort in
I have
linear
no idea what
time. We
that
can
is.
sort this input array in linear time. Reason being is we know that there's only 3 different buckets. If the values ranged from 0 to, n, where n could be an arbitrarily large value, then of course we could not do this in O of n time, but we know the values are only going to be between 0 and 2. We can do bucket sort. Now, what is bucket sort? And how are we going to use it to solve this problem in linear time? Well, we're going to say we have 3 buckets, a 0 bucket, a 1 bucket, and a 2 bucket. And for each of these buckets, we're simply going to scan the input array and count how many of each of these values occur in the array. So yes, we are going to need extra memory, but really this is just going to be, let's say, a hash map or an array of size 3, right? This is just going to be an array of size
Okay, I
3.
think this is what
So
I
we'll
did.
count how many 2s. So we have a
This
single
bucket
2
sort
so
thing.
far. We have a single 0. We have another 2. So let's say the number of 2s is 2. Then we get 2 1s. So yes, we have 2 1s, and then we get another 0. So in reality, we have 2 of each of these values. Now we want to build the output array, but we are not going to create a separate output array. They want us to do this in place. We can see up above. So what we're just going to do is, since we know we have 2 zeros, let's just go at the beginning first 2 values, cross these out, replace them with 2 zeros, just like in the output array. Again, so now we're done with the zeros portion, right? We took 2 zeros, put them at the beginning. Next, we know ones go right after zeros, so we're going to take these 2 ones, cross out these 2 values, right? And then add 2 ones right after the zeros. And the exact same thing with the 2s, right? We have 2 2s, so that's going to make up the remaining portion of the array. We can place those 2 2s.
Okay, I want to just do something real quick. Because in my submission, my memory was pretty bad, I think. Okay, wait, how is it 83%? But there is something I want to try. Instead of just creating all these lists, kind of just do something like this. Just say k equals 0. And then we just have 3 for loops. For I in range table dot get 0, we just do why did I type it there? nums k is equal to 0, k plus equals 1. Let me just get rid of all this. And then you just change this to this, this to this, this to this, this to this. And I think this should just be the same thing, if I'm not mistaken. Yeah. And we should have cut. Okay, somehow we didn't cut down on memory. How though? Are we not using less space? We didn't create we didn't create 4 entirely new arrays. Okay, you know what? Maybe I just don't know anything. Let's just watch the rest of the video.
End, right? So we're overwriting this memory. So we're not actually using extra memory or anything. So this is a O of n time solution and O of 1 solution. This solution, in terms of complexity, is about as good as it gets. But this is such a trivial solution that I'm actually going to show you the slightly more hard solution, which is actually the one-pass solution. We can see in this case we actually
I wanted to do this one.
array
this is
twice,
the one with the
once to create these buckets,
I
and then
know
once
how
to
to do
actually
the
build the
bucket
output
sort.
array. But we can technically do it with a single pass, which is a slightly harder solution. That's what I'm going to show you today, and that's what we're going to code up. So before I show you the solution, my first question to you is, have you heard of the algorithm quicksort? In particular, do you know the portion of quicksort that requires the partition algorithm?
So.
Do you?
And there's 3 pointers, I think. And like one of them is a pivot, and you choose a random pivot. I don't know. I think the thing is, my class had a weird implementation of quicksort. I think there's like multiple implementations, so I don't fully remember how it works, but I'm gonna listen to what he says.
You know how to partition an array. For example, you know, let's say we had an array and we wanted every single value, n value, which is less than 5, to go in the left portion of the array. And if we did that, let's say we had an array of 1, 2, 6, 7, right? These values, we wanted the values that are less than 5 to go in the left portion of the array. If we did that, what does that mean? Well, that means we took these values, put them in the left portion of the array. Now, if we did that by swapping values around, if these 2 values are over here, and let's say the size of the array is 4 values, these original 4 values, if we took these and put them in the left, that means by default, these 2 values, which are greater than or equal to 5, are going to go in the right portion of the array by default, right? That's called partitioning an array. That's the same idea we're going to use here. So remember how we want the zeros to go at the beginning, we want the ones to go in the middle, and 2s to go at the end. So let's partition the array using the same idea. We're going to go through every single value in the array, right, in the example array, let's say, and every time we get a 0, the way this partition algorithm works is we have a single pointer at the left, right? It's basically, we're going to call this, let's say, the left pointer, right? It's designated beginning all the way at the left. We're going to have another pointer, I, which is just going to be running through the entire array. Anytime we get a 0 value, we're going to take that 0 value, let's say it's from over here, we're going to take that 0 value, swap it with the value that's over here, right? The value that's over here is not going to be a 0, right? So whatever it is, maybe it's a 1, maybe it's a 2. Either way, we're going to swap it, put it over here, and then that 0 is going to go over here. So then once we have a 0 value here, and then
I just want to rewind.
So let's partition the array using the same idea. We're going to go through every single value in the array, right, in the example array, let's say, and every time we get a 0, the way this partition algorithm works is we have a single pointer at the left, right? It's basically, we're going to call this, let's say, the left pointer, right? It's designated beginning all the way at the left. We're going to have another pointer, I, which is just going to be running through the entire array. Anytime we get a 0 value, we're going to take that 0 value, let's say it's from over here, we're going to take that 0 value, swap it with the value that's over here, right? The value that's over here is not going to be a 0, right? So whatever it is, maybe it's a 1, maybe it's a 2. Either way, we're going to swap it, put it over here, and then that 0 is going to go over here. So then once we have a 0 value here, then we can take our left pointer and then shift it over here, right? Because then we know that the next time we encounter a 0, we want to put it in this position. Now, of course, what happens if the first value by itself already is 0? Then we're going to end up swapping it with itself, which is perfectly fine, and then we're going to take our left pointer and then shift it here anyway. So it works out in both cases. So let's say we do that. Let's say we run through the entire array. What's our array going to look like? Well, in this example, we'll have 2 zeros being at the beginning, but then we'll have the remaining portion just being some 1s and 2s in some arbitrary order, right? We don't know about the order of these. So we successfully partitioned the array. We got all the zeros at the beginning, right? This is one partition. Now we still need to like partition this, right? We need to put both of these 1s at the beginning and then take all the 2s and put them at the end, right? But remember, if we do it like this, then we are doing 2 passes, right? It's technically allowed, but our target was to do this in a single pass. So let's maybe try to modify this partition idea. How about we take all zeros, put them here using our left pointer, but why not have a second pointer, which is always going to be at the right, let's call it our right pointer, and then anytime we encounter a 2, we put the 2.
Okay. I think I know how this works now. You have 3 pointers. You have L at the start, R at the end. I goes through, it sort of like iterates through the whole thing. If I hits a 0, and swap with L and then increment L, right? If I hits a 2, then swap it with R and increment R. And if it hits a 1, then increment I. I think that's what he's about to say. But let me just keep watching.
Anytime we encounter a 0, we put the 0 over here. We shift our left pointer accordingly. If we end up putting a 2 here, we take our right pointer and shift it accordingly to the next position. So this idea is definitely going to work, but there's just one edge case we have to worry about, and let me just show you that edge case. Let's say we got to some random scenario where our left pointer is going to be over here, designating to us that everything to the left over here is already a 0, right? That's of course what the left pointer is going to tell us. If it's over here, that means everything over here is going to be a 0. That makes sense. And our right pointer is going to be over here, which is going to designate to us that everything to the right of it is supposed to be a 2, which makes sense. That means there was some arbitrary 2 that we found in the array. We moved it over here, and then we took our right pointer and then shifted it by 1 over here, right? And every time we encounter a value, like we have our I pointer over here, we're going to put this wherever it needs to go, and then we're going to shift our I pointer to the next position, right? But there's one thing that we have to worry about. Take a look over here. Our left pointer could be pointing at a 1 value, right? Because if we encounter a 1 value, we're just going to skip it, right? Then our I pointer could be over here. Let's say our I pointer is here in this example. Our left pointer, yes, could be pointing at a 1, but notice how our left pointer is never going to be pointing at a 2, because if it was, we would have already swapped it and put it towards the right, right? Because see how our I pointer has already passed this position. So if it was a 2, we would have already swapped it over there. Since it's not, that must mean it's always going to be a 1, which is good for us. But you'll notice with the right pointer, everything to the right over here is going to be a 2, but the right pointer could be pointing at a 0, or it could be pointing at a 1, or it could even be pointing at a 2 maybe, right? And if it's pointing at a 0, that's going to be a problem for us. because watch what happens now. Our I pointer is over here. We see a 2. What do we do with 2s? We swap it with the right position, right? So let's perform that swap. Let's cross this out, change it to a 0, cross this out, change it to a 2. Then we're going to take our right pointer, shift it over here, right, which designates to us that this portion is going to be all 2s. That's perfectly fine. And now we're also going to take our I pointer and then shift it to the right. But now notice what we just did to our array. See how the zeros are not all the way at the left, right? We took a 0 and then moved it into the middle of the array. So the reason I went through this long explanation is basically to tell you is that if we take a value and swap it with the right pointer, it could potentially introduce a 0 in the middle of our array, which is something we don't want to do. So in that case, if we do that, we don't want to shift our I pointer. So what I'm saying is, if we ever encounter a 2 value like this one, yes, we're going to swap it with the right pointer, but in that case, we're not going to increment our I pointer. That's not going to be the case if we find a 0 and then swap it with the left pointer, because our left pointer is only going to be pointing at a 1 value. So if we take a 1 value and then introduce it into the middle of our array, that's perfectly fine because 1s always go in the middle. But we can't take a 0 and put it in the middle. That's not going to work. So that was a pretty long explanation, but I hope that you do get the idea. The code is going to be a lot easier. So let me just run through the rest of this example. So we encounter a 2. So we are going to swap it. So we're going to put the 0 here. We're going to put the 2 over here. And then we're going to take our right pointer, shift it to be in this position. And we're not going to increment our I pointer. Of course, the left pointer is not going to be incremented. We don't have to do anything with it. But since we performed a right swap, I stays the same. So now we're going to look at, again, what value is in this I location. It's a 0. So in this case, yes, we are going to swap it in the left position. So let's do that. Let's cross this out, put the 0 over here, and then put the 1 over here. So it's gotten pretty messy, but ignore that. So since we performed a left swap this time, we're going to take our left pointer, increment it by 1. So left is going to go over here now. And we're also going to take I and increment it by 1, right, to be in the next position over here. It's going to be at the 1. We don't have to do anything with a 1. We don't put it in the left, and we definitely don't put it in the right. 1s are
So what's
just
the
ignored.
end condition
So then I is
when they
going to be
overlap?
incremented one more time until I is in this position. And once our I pointer surpasses our right pointer, we're done, right? Because we know that the portion to the right of the right pointer is going to be sorted anyway. It's going to be all 2s, right? So now we're done. If you take a look at our output array, it's a little bit messy, but let me just kind of draw this. It's sorted, right? 0, 0, 1, 1, 2, 2. So let's dive into the code now. Okay, so now let's write the code. Like I said, we're going to have 2 pointers, a left pointer at the beginning and a right pointer all the way at the end, which is going to be nums, length of nums minus 1. And we're also going to have a third pointer, I, which is just going to iterate through the entire array until we exceed our right pointer. So while I is less than or equal to right, let's continue. So there's 2 cases we worry about if the value that we're at is either a 0 or if the value that we're at is a 1. So if nums of I is equal to, or maybe I said 1, but if nums of I is equal to 2, right? That's our right case. So in both of these cases, we're going to perform a swap, right? Since we're doing a swap in both of these cases, I don't want to write it out, so I'm just going to define a helper function up above.
Okay, yeah.
So,
So wait, I had that idea. Right? You know, I had the idea here to create like a swap function. I think I just didn't think of using 3 pointers because I was so fixated on, you know, this is 2 pointers. So I was like, oh, there's only 2. There's only a left and a right, but there's actually
indices 3 of nums that
I
we're
think
going
that
to be
was the
swapping.
problem.
So let's just get a temp value for nums of I. The reason I'm not passing nums into this function is since this function is defined inside of another function, we actually aren't required to pass in that variable. It has access to any variables outside of it. So let's get nums of I, store it in temp, and then replace nums of I. So if I equals 0, then that means we're swapping this with the left pointer. So let's run swap on our left, so we're going to increment our I pointer. And then outside, we don't have to return anything. We just have to modify the nums array in place, which is exactly what we did with our swap function. So this is the entire
why is
code.
I minus equal 1? So if nums I is equal to 2, you swap I and R. Decrement I. Right, decrement I. Let me get to that part.
Equal to 2. In that case, we're going to also be doing a swap, but we're going to be doing the swap with our index I and our right pointer, right? And if we do that, then we have to take our right pointer and decrement it by 1. Now, in either case, remember, we want to increment I every single time, but remember, if we performed a right swap, we don't want to increment I. So in this case, I'm just going to say, but if we encounter a 2, remember, we don't want to increment our I pointer. So in this case, I'm just going to do the opposite. I'm going to decrement I, and that's going to be canceled out by the incrementing operator right outside of it, which is going to execute every single time. So if we encounter a 1,
Why do
we're
we
not
need
going
to do that?
enter either of these conditions.
Why in a right swap do we not need
But we are still going to increment our I pointer. And then outside, we don't have to return anything. We just have to modify the nums array in place, which is exactly what we did with our swap function. So this is the entire code. You can see that it's very efficient. This is the one-pass solution. So I hope that you found this helpful. If it was, please like.
Okay, I understand everything except that one thing about decrementing the I pointer in a right swap.
But in that case, we're not going to increment our I pointer. That's not going to be the case.
Wow, I managed to skip right to it.
Which is something we don't want to do. So in that case, if we do that, we don't want to shift. It could potentially introduce a 0 in the middle of our array, which is something we don't want to do. So in that case, if we do that, we don't want to shift our I pointers. So introduce a reason I went to pointer and then is just opening. One left pointer could be pointing at a 1 value, right? Because if we encounter a 1 value, we're just going to skip it, right? Then our I pointer could be over here. Let's say our I pointer is here in this example. Our left pointer, yes, could be pointing at a 1, but notice how our left pointer is never going to be pointing at a 2, because if it was, we would have already swapped it and put it towards the right, because see how our I pointer has already passed this position. So if it was a 2, we would have already swapped it over there. Since it's not, that must mean it's always going to be a 1, which is good for us. But you'll notice with the right pointer, everything to the right over here is going to be a 2, but the right pointer could be pointing at a 0, or it could be pointing at a 1, or it could even be pointing at a 2 maybe, right? And if it's pointing at a 0, that's going to be a problem for us. Because watch what happens now. Our I pointer is over here. We see a 2. What do we do with 2s? We swap it with the right position, right? So let's perform that swap. Let's cross this out, change it to a 0, cross this out, change it to a 2. Then we're going to take our right pointer, shift it over here, right, which designates to us that this portion is going to be all 2s. That's perfectly fine. And now we're also going to take our I pointer and then shift it to the right. But now notice what we just did to our array. See how the zeros are not all the way at the left, right? We took a 0 and then moved it into the middle of the array. So the reason I went through this long explanation is basically to tell you is that if we take a value and swap it with the right pointer.
I see why. Okay. So if you do that, if you swap I and R, then there's a chance that you end up with a 0 here. Right here, right? And then you increment I. And then there's no way to swap this 0 with this L, right? Because your I pointer is already moved past. You can't do that. And the reason it's not like vice versa. Like the reason I was confused, I was like, okay, so you don't decrement it for a right swap, but how is a right swap any different than a left swap? The difference is this I is going from left to right, so it's seeing every value here. So the problem is we don't want a 0 to end up in the middle of the array, but we're never going to have a 2 end up in the middle because I is moving from left to right. So any 2 we see will automatically be swapped to the end. It'll never be swapped here. There will never be a 2 at the start of the array that we accidentally swap into the middle. Because I will catch up to it eventually, right? So I think that makes sense. Let me try to code this up. So we did the bucket sort solution by accident, I guess. Let me try to code this up. If I can remember the intuition, this is my test. So if I know how the algorithm works, I should be able to code it, right? So, okay. So we have a left and a right pointer, right? So L and R, let's call it left, right to 0. I like doing it like this. And we also have I. Where does I start? I guess I also starts at 0, right? I is equal to 0. And so now we need a loop. Well, I is less than R. Because once I crosses R, well, R maintains the beginning of the right sorted array. So if I gets past R, those I's are already sorted. We don't need to do any more swaps. In fact, when I is less than or equal to R, it should be. Yeah. So there's two cases, right? So if okay. So if nums I is equal to 0, this is a left swap. I think we need to code this swap as well. Def swap say comma b. This is relatively simple, right? Temp is equal to nums a equal to nums b nums b is equal to temp. That's easy. Then, so if I is equal to 0, you're going to swap left, comma I, and then we increment left. If nums I equal, and the reason we're doing elif here, we don't need to do else, because if nums I is equal to 1, then we should just increment nums I. We don't actually do anything, we kind of just stall. So now we need to do swap right and I, then we decrement the right pointer, and then we also need to do I minus equals 1, because here we don't want to accidentally swap a 0 into the middle of the array. So if right decrements, we need I to stay in place so we don't accidentally pass over a 0 value. And I think this should work. So let me just run it. I probably made a mistake. Okay, what did I do? What did I do? Oh, I did not mean to put that. That needs to be See, this is why I don't do these things at like 2 a.m. But I kind of just ended up doing it anyways. Okay. You know what? This is actually the exact thing that we got when we did bucket sort. But it is less memory overhead, I guess, because in bucket sort you need to create a hash table. For this you don't. I think it's a good ending point, honestly. I'll let me add to here. Problem. Show its pointers in because I assume I can't type. Two were needed. Coded the bucket sort solution on my own. Understood the. I guess this is called quicksort partition. With help coded eventually. What? How do I just create a new line? You know, I'm not even gonna ask. How do I just insert a new line? Like, hello? Did no one like invent that yet? Okay, just enable text wrapping for this. But yeah, I mean that's pretty much it. Oh, yeah. Arrays. Let's see what progress we've made. So we did 2 pointers. Yeah, I'm gonna try to do this one tomorrow with minimal help. I think I know how to do this one already, or I can do it pretty fast. So maybe we'll knock out those 2. We'll try to do 2 in one video maybe tomorrow. Um, I mean, I was supposed to finish arrays today, so the rest of this schedule, this is gonna end up getting pushed back, which I kind of anticipated. Like, there's no way I would finish everything in just May, because I have to learn stuff. Like, I should allot like half my time for reviewing. Like, I only have like 28 days to review. It's 100 days in total. So this can essentially be doubled the time for like training. So I'll fix that scheduling and stuff eventually. I think that's a good end for now. This video is about like an hour long. I think I learned a lot though. Like the whole partitioning stuff. That makes sense. And the only way to really get better at it is just doing more problems. So yeah, I will see you guys in the next one.